Assalamu alaikum class. We have covered Q data structure in detail. Now before moving toward our next data structure, that is tree data structure, we will cover a topic named as recursion. What is recursion? A recursion is a repetitive algorithm, that is a code that need to be run over and over again. In general, there are two approaches to writing repetitive algorithm. One is iteration or loops and second is recursion. To get better understanding, we will solve a problem by using these two techniques, iteration and recursion. Let's consider a function that calculates the factorial of number. So what is the factorial of number? The factorial of the number is the product of all integers from 1 to that number. For example, factorial of 4 is 1 multiplied by 2 multiplied by 3 multiplied by 4, that is equivalent to 24. So in general, the iterative definition of the factorial function is as follow. If n is equal to 0, if number is equal to 0, then factorial of that number is equivalent to 1. And if n is greater than 0, then we need to take the product of all the integer from 1 to that number, like n into n minus 1 into n minus 2 and so on. So this definition is iterative because the definition only contains the algorithm parameters, not the algorithm itself. You will understand it better if we see the recursive implementation of the factorial function. Here is the recursive definition of the factorial function. If the value of the n is 0, then the factorial return is 1. So if the value of the n is greater than 1, then we call the function with n minus 1 value again. And we multiply that answer with the n. So what was the difference between these both definition? In iterative definition, function does not call itself, while in recursive definition, function call itself. Now we know the difference between iteration and recursion. Let's see how recursion works. We will solve a simpler example, that is factorial of 3. We will start from the top level, factorial of 3, and simplify the problem into the 3 multiplied by factorial of 2. Now we don't know what is the answer of factorial of 2. We call the function factorial of 2. Now we have a slightly less complicated problem, that is factorial of 2. We simplify this problem into 2 multiplied by factorial of 1. And we continue this process until we are able to reach the problem that has a known solution. In this case, the known solution is factorial of 0. We know that if the value of n is equal to 0, then answer is 1. So the function then return in reverse order to complete the solution. We will return the answer of factorial of 0 to the calling function. So we can calculate now factorial of 1. Factorial of 1 is equal to 1 multiplied by 1 is equal to 1. So we will return the answer of factorial of 1 to the calling function. Now we can calculate factorial of 2, that is 2 multiplied by 1 is equal to 2. 2 is returned to the calling function and then we can calculate the factorial of 3. 3 multiplied by 2 is equal to 6 and that is your final answer. Every recursive definition has two parts. The one is base case, another is generic case or general case. The noun solution of the recursive definition is the base case. In the previous example, in the case of factorial function, the base case was factorial of 0 equivalent to 1. If the value of the n is 0, the answer will be 1. That was the noun solution. So every recursive algorithm must have a base case to simplify to. Otherwise, the algorithm would run forever and turn into an infinite iteration or until the computer ran out of memory. Recursive definition has two parts. We know what is the base case. Now what is the generic case? The part that solves the problem into the smaller or simplify the problem toward the base case is known as general case. In the previous example, 3 multiplied by factorial of 2 or 2 multiplied by factorial of 1 is the general case of the recursive definition. After looking at both iterative and recursive methods, it appears that a recursion or recursive method is much longer and more difficult. If that is the case, then why would we ever use recursion? It turns out that the recursive technique, although more complicated to solve by hand, but are simple and elegant to implement in a computer. Now that we know the differences between an iterative algorithm and a recursive algorithm, we will develop both an iterative and recursive algorithm to calculate the factorial of a number, and then we will compare these two algorithms. This is the iterative algorithm of factorial function, a very straightforward approach. We simply loop through all the integer between 1 to that number and multiply them together. And this is a recursive algorithm of factorial function. If n is equal to 0, we will return 1, else return n into call the function again with n minus 1 value or the simpler problem. Note how much simpler the code for the recursive version of the algorithm is as compared to iterative version. We have eliminated the loop and implemented the algorithm with one if else statement. So, how recursion works? To truly understand how recursion works, we need to first explore how any function call works. When a program calls a subroutine or a function, the current function must suspend its processing. The called function then takes over control of the program. So, when the function call is finished, it needs to return to the function that called it. The calling function then wakes up and continue its processing. So recursion use tag. Why? Because when a function is called, some information need to be saved in order to return the calling module back to its original state. So we need to save information such as local variable or the spot in the code to return after the called function is finished. To do that, in recursion, we use tag. Well, good news for you guys, you don't need to use user defined stack. A built in stack is available, known as system stack. Before function is called, all the relevant data is stored in a stack frame by the system itself. You don't need to do anything for that. This stack frame is then pushed onto the system stack. After the called function is finished, it simply pops the system stack to return to its original state. So by using a system stack, we can have function calls other function which can call other functions and so on. Because the stack is last in first out or first in last out data structure, as the stack frames are popped, the data comes out in a correct order. So now the question is how one can design its own recursive algorithm. To do that, you need to take care of two parts. The one is journal case or generic part, a part that reduces the size of the problem, and the other is base case, a part that solves one part of the problem. Every call to a recursive algorithm must either solve a part of the problem, base case, or reduce it in size, that is, journal case. To design a recursive algorithm, you need to remember these design rules. Number one, determine the base case. You must have a base case or a stopping condition. If not, then your algorithm will run infinite. And second, determine the journal case that either solve the problem or simplify the problem and combine the base case and the journal case into an algorithm. When combining the two parts of the algorithm, we must make sure that we either reduce the size of the problem or move it closer toward the base case or reach the base case. So, what are the advantages of recursion? Or you may be thinking, why are we studying this topic? You will get the answer when we move toward our next data structure. Because recursion is a very powerful problem solving technique that often produces very clean and simpler solution to even the most complex problem. It gives the easier solution that is easier to understand and to describe than iterative solution. Like any other data structure or any other solution of the problem, there are also some limitations. So, what are the limitations of recursion? By using recursion, you can often write a very simple, short implementation of your solution. However, just because an algorithm can be implemented in a recursive manner doesn't mean it should be implemented in a recursive manner because recursion works the best when the algorithm or the data structure that is used naturally support recursion. One such data structure is the tree, and we will move forward to a tree data structure. And one such algorithm is binary search tree. Another limitation of recursion is of system call. We know that in backend we use stack and stack frame. So whenever we call a function, there is an extensive overhead because of the calls. When a call is made, we need to build a stack frame, and then that stack is pushed onto the system stack. And this will take time, and this will increase overhead on the processor. Similarly, when the stack frame is popped from the stack, the local variable must be reset to its previous position, and that will also take time. So these are the limitation of recursion.